V3, V2, W2, V1, W1, V0, W0. Tell me the coefficient of the expansion. V0. What is the coefficient here? 5. What's that coefficient? -1. Alright? How about this one? It will be 4, 6. Right? 4, 6. How about W1? -2, 1. Okay, now V2. 2, 6, 7, 5. How about V2? -1, -1, 0. And V3, you know, right? It's 1, 3, 5. It's 1, 3, 5, 7, 7, 7, 5. Any of these that you choose have 8 coefficients. If you choose the first choice, V3, you have 8 numbers to represent that, right? And those are numbers that you use to reconstruct. Okay? If you choose the second choice, V2, W2, how many coefficients do I have? 8. Right? 4 here and 4 there. It's still 8. Okay? If you use the third choice, what do I have? V1 and these two guys. 2 plus 2 is 4. 4 plus 4 is 8. Alright? The third choice, the last choice, we have 2, 3, 4, 5, 6, 7, 8. They all have 8 coefficients to choose. Which one's better? It's not the number of coefficients. It's how much change in the coefficient. Right? So let's think about, if you want to code. If this has high and then grade. Look at this. 5, and then this is very, very small. Right? So if you use the third one, for example, if you have to truncate, right, or quantize, this is better than quantize. Because they're quite small. Okay? So if I'm looking at this one, right, you can think of this as, if you have a coarse approximation, it's basically the average. It's 5. It's 5 plus 7 plus 5 plus 3 plus 1. That's going to be about 8. Right? That's the average. Right? That's what you how you represent. Taking the average first, and then you have the details coming in, right? You have this detail, that one, and this one. Depends on what you need to send. Okay? So if you only can see, in the low pass, coarse approximation, you might want to send only number 5. And that will be your signal to represent. If you need a high resolution, I want to send 5 and 5 and this coefficient. I give you this. I have 4 and 6 now. Slightly more details. It's not good. It's good. If it's more information, now I have to send this 2, right? 2 and 1. And I got this. More details now. Okay, more structure. If I need even more, then I'm sending, -1, -1, 0, 0. And I get back to this one. Okay? So this is basically multi-resolution. That's an example. You see all the basis functions are associated with this. The nice thing here is that the basis function has scale. Right? We have phi of t. I only have to know phi of t and w of t. The scaling function is called scaling function, and this is called wavelength. For every dyadic wavelength system, there's a scaling function associated with the low pass operation. There's a wavelength associated with the high pass details operation. And I only have to know 2 of them, phi of t and w of t. Because the basis function for the order scale, the order resolution is related, right? Phi of t, phi of 2t, phi of 4t, phi of 8t, and so on. and vice versa for W of t. Any question? Which space is bigger? Which space is bigger than the other space? I'm comparing the space, the span of that space. Who think V0 is bigger? Who think V1 is bigger? V1 is bigger, right? The V1 space is a space that captures half. This y constant with half unit interval. V0 is the whole unit interval. So obviously a half, you can build two halves, right? Become one. So very, you can see that V1, V0 can be 1, right? And so on. And V1 can be 2. And so on. Okay? V0 and V1. What is the basic function of V0? P of t, right? What's the basic function in V1? P of 2t. Tell me how to write this statement using basis function. V0 in V1. Okay? I know that the basis function in V0 is P of t. And the basis function in V1 is P of 2t. How do I translate that statement using basis function? If I can represent P of t using a combination of P of 2t minus k, let's call this H naught of k. With a scaling, okay? If I can find a set of number H naught, so that this is true, then I'm done, right? It's saying that I can represent a basis function in V naught in terms of V1. It means that V naught in V1. Right? Because basically, if I know, this relationship, if you give me anything in V naught, I can plug into here, and I'm done. Right? If I know a signal x of t is phi of t plus 7 phi of t minus 3, what do? I take phi of t, I plug into here, right? I got something in phi of t minus k, right? I got t minus 3, I plug to minus 3 here, I got minus 3, okay, and so on. Okay, so it means that I can write x of t in phi of 2t. Okay? Alright. And how about W, 0, and V1? Which space is bigger? 0 is right here. Right? And V1 is right there. Which space is bigger? V1. W0 in V1. Which means that the basis function in W0, which is the wavelet W of t, can be represented as linear combination of the basis function in V1, which is here 2t. This is called the refinement equation. It means that if I choose an H naught H1, and H naught here is basically the low pass filter in the filter bank. Okay? H1 is a high pass filter in the filter bank. If you give